In a world where scientific theories are frequently accepted as unquestionable truths, an unexpected figure arises to challenge the foundations of our understanding of the universe. Terrance Howard, the charismatic actor known for his roles in blockbuster films and acclaimed TV series, emerges beyond the glitz and glamour of his artistic career with a profound fascination for the mysteries of existence. This fascination leads him to question the status quo and propose that everything we know about the origin of the universe might be wrong. Howard suggests that the Big Bang Theory, considered the cornerstone of modern cosmology, may be just one piece of a much larger and more complex puzzle. His provocative statements ignite curiosity and controversy, urging us to rethink what we accept as truth. He invites us to explore the possibility that our current understanding is limited and that new discoveries may reveal a universe vastly different from what we imagine. By questioning these established truths, Howard reminds us that scientific knowledge is always provisional, subject to change with new evidence. This critical and inquisitive stance is essential for the advancement of human understanding, as it encourages us to look beyond the boundaries of current knowledge and consider alternative perspectives that may lead to a deeper understanding of the cosmos. In summary, Terrance Howard, with his intellectual boldness, challenges not only traditional scientific theories but also inspires us to maintain an open mind and to continue exploring the mysteries of the universe. It is in this spirit of inquiry and discovery that we find the true drive of science and philosophy. Terrance Howard's provocative statements, asserting that time has no beginning and dismissing the Big Bang Theory, have sparked curiosity and controversy. In a scenario where science is constantly reshaped by new discoveries, the James Webb Space Telescope, JWST, steps in, providing new evidence that challenges the validity of the Big Bang Theory. Recent images captured by the JWST reveal galaxies that are smaller, smoother, and older than predicted by the Big Bang Theory. This observation suggests that our understanding of the universe's expansion may be flawed. According to the traditional theory, as the universe expands, galaxies should appear larger due to the stretching of light with increasing distance. However, JWST images show the opposite. Galaxies with high redshifts, which should appear larger, actually appear smaller. This discovery is causing significant reassessment among cosmologists and astronomers. The discrepancy between the predictions of the Big Bang Theory and the observations of the JWST raises profound questions about our understanding of the cosmos. If the observed galaxies are smaller and older than believed, this implies that the universe may not be expanding in the way we imagined. These revelations invite us to consider new theories and models that may explain these anomalies. Science, at its core, is a process of constant revision and refinement, driven by new evidence and observations. The challenge posed by the JWST's discoveries exemplifies this process, encouraging scientists to question established assumptions and explore new possibilities. In this context, Howard's assertions take on a new dimension. By suggesting that time has no beginning and that the Big Bang may be just a part of a more complex puzzle, he encourages us to broaden our horizons and consider that the true nature of the universe may be much more intricate than our current theories allow. It is this openness to the unknown that propels scientific and philosophical progress, leading us to a deeper and more comprehensive understanding of cosmic reality. The implications of the James Webb Space Telescope's discoveries are profound and potentially revolutionary. The characteristics of galaxies captured by the JWST directly contradict the expectations of the Big Bang Theory. These smaller and smoother galaxies challenge the idea of a uniform and consistent cosmic expansion. If the Big Bang Theory were correct, these distant galaxies would have to be exceptionally small to fit into the current model, which seems increasingly implausible. Furthermore, JWST images reveal that even the most massive and brightest galaxies are 2 to 3 times smaller than previously thought. This raises serious questions about the accuracy of the Big Bang Theory. How can we reconcile these new observations with the theory that has long served as the basis for our understanding of the universe? This discrepancy suggests that we may need to reconsider our cosmological models and make room for new interpretations. Science, in its relentless pursuit of truth, must be flexible enough to adapt to new evidence. The JWST's discoveries indicate that the universe may be much more complex and diverse than we imagined. The implications of these discoveries extend beyond cosmology. They force us to reassess our conceptions of galaxy formation and evolution, the nature of time and space, and even the fundamental laws of physics. The possibility that the universe is not expanding in the way we believed suggests that other unknown forces or phenomena may be at play. In this context, Terrance Howard's questioning of the nature of time and the origin of the universe gains renewed relevance. His willingness to challenge established theories and consider alternative possibilities reflects an inquisitive spirit that is essential for the advancement of knowledge. The discoveries of the JWST remind us that science is a field in constant evolution, where new questions arise as old ones are answered. It is this dynamic that leads us to explore the mysteries of the cosmos more deeply, with the hope of unraveling the true nature of the universe. Ultimately, openness to the unknown and willingness to question the established are what propel us to new frontiers of understanding and discovery. The recent discoveries of the James Webb Space Telescope, JWST, not only challenge our understanding of the expansion of the universe but also lead us to question the very nature of time and space. Some scientists, including Terrance Howard, have begun to consider the possibility that time may be an illusion created by human memories. They argue that everything that has ever happened or will happen is, in fact, happening simultaneously. This perspective challenges the traditional view that time moves in a strict and linear direction, from past to future. Instead, the block universe theory, supported by Albert Einstein's theory of relativity, suggests that past, present, and future coexist simultaneously in a four-dimensional structure of spacetime. In this model, all events exist permanently at their respective locations in spacetime, and our perception of movement through time is merely an illusion. This radical idea has profound implications for our understanding of the universe. If time truly does not flow but is a fixed dimension like space, this would fundamentally change our perception of reality. We could then see the universe as a static tapestry, where what we call past and future are just different regions of this tapestry. This view may seem counterintuitive, but it opens up new possibilities for exploring the nature of existence. The notion that time may be a mental construct also resonates with various philosophical and spiritual traditions, which have long suggested that time is an illusion. This convergence of scientific and philosophical ideas may help us develop a more holistic and integrated understanding of reality. However, this perspective also presents significant challenges. If time is an illusion, how do we explain the sequence of events we experience in our daily lives? How do we reconcile this view with the laws of physics that depend on the flow of time? These are complex questions that continue to intrigue scientists and philosophers. The proposal that time may be an illusion invites us to reconsider our most basic assumptions about reality. It is an invitation to explore new ways of thinking about the universe and our place within it. The pursuit of truth requires the courage to question even the most deeply ingrained beliefs and the willingness to embrace the uncertainty and complexity of the cosmos. Thus, we continue to investigate, always open to new discoveries that may transform our understanding of time, space, and existence. In addition to criticisms of the Big Bang theory, other emerging theories propose new ideas about the nature of spacetime, challenging our current understanding. Among these, loop quantum gravity and string theory stand out. While Einstein's general relativity describes spacetime as a continuous and smooth structure, loop quantum gravity suggests that it is composed of tiny loops, forming a kind of microscopic web. This view proposes that at extremely small scales, spacetime is granular, not smooth. String theory, on the other hand, imagines that fundamental particles are not points but rather tiny vibrating strings. Each type of vibration of these strings would correspond to a different particle. This theory is appealing because it potentially unifies all the fundamental forces of nature, including gravity, into a single theoretical framework. However, it requires the existence of multiple extra dimensions beyond the 4 we know, 3 spatial and 1 temporal. Both theories face the monumental challenge of being empirically tested due to the tiny scale at which they operate. To verify loop quantum gravity, we would need technology capable of probing distances smaller than the smallest fractions of an atom, which is currently beyond our capabilities. Similarly, testing string theory requires energies much higher than what we can achieve with our current particle accelerators. The search for a unified theory that combines general relativity with quantum physics is one of the greatest challenges of modern physics. General relativity works exceptionally well in describing phenomena on large scales, such as planetary orbits and the structure of the universe. Quantum physics, on the other hand, accurately describes the behavior of subatomic particles. However, the two theories are fundamentally incompatible in their current forms. Scientists are exploring various approaches to resolve this incompatibility. Non-commutative geometry, for example, suggests that spatial coordinates may not follow the conventional commutation rules of mathematics, introducing a new structure to spacetime. Dynamic causal triangulation, on the other hand, attempts to build spacetime from elementary blocks called samplices, creating a network that evolves dynamically. These new theories and approaches represent exciting and promising advances in our quest to understand the universe. They remind us that science is a dynamic and ever-evolving endeavor, where each discovery brings us closer to the ultimate truth about the nature of reality. With each new theory and each new experiment, we advance in our understanding of the cosmos and our place within it, continuously challenging our assumptions and expanding the limits of human knowledge. The discoveries of the James Webb Space Telescope, JWST, are prompting a profound re-evaluation of many ancient beliefs about the universe. The well-formed structures of tiny galaxies and the existence of very ancient galaxies challenge the idea of a universe in constant expansion, as proposed by the Big Bang theory. Furthermore, the abundance of galaxies found in deep space and the new questions about the nature of time indicate that our understanding of the cosmos is in a state of continuous flux. These new insights underline a fundamental truth of science: knowledge is provisional and always subject to revision with the arrival of new evidence. The history of science is filled with revolutions that radically transformed our view of the world. From Copernicus' heliocentric model, which shifted Earth from the center of the universe, to Einstein's theories of relativity, which redefined our understanding of space and time, each advancement was driven by a willingness to question the established and explore the unknown. As we continue to explore the mysteries of the universe, it is inevitable that our theories and models will be challenged and refined. The discoveries of the JWST are a powerful reminder that there is still much to learn. They encourage us to keep an open mind and embrace uncertainty as a natural part of the scientific process. The future of science promises new and exciting discoveries that may profoundly change our perception of time, space, and existence itself. The quest for a unified theory that reconciles general relativity with quantum physics, investigations into the granular nature of spacetime, and the exploration of additional dimensions are just some of the frontiers we are beginning to explore. Each discovery not only expands our knowledge but also inspires us to ask even deeper questions. By questioning our assumptions and exploring new possibilities, we advance not only in terms of scientific knowledge but also in our philosophical and spiritual understanding of the universe. Ultimately, scientific progress is a testament to the human spirit of curiosity and exploration. As we continue to unravel the secrets of the cosmos, we are constantly reminded that the journey of knowledge is endless. And it is this journey, filled with intriguing questions and surprising discoveries, that leads us to an ever deeper understanding of reality. Looking to the future, we can expect many more scientific revolutions that will transform our view of the universe and our place within it.